So in this video we're going to look at the graph of the logarithm function, and we're going to begin first with what we know already, which is the exponential function. In this case, a growth graph, y equals 2 to the x. I have a table of values in the graph shown. And just remember that properties of the exponential function: the domain is all reals, the range is greater than 0, at y equals 0 there is a horizontal asymptote. An exponential function has no x-intercepts, but it has 1 as its y-intercept, and it has no vertical asymptotes. Now what I want to do now is I want to graph the inverse of y equals 2 to the x, and that means to switch the coordinates of x and y, to switch the domain and the range. So the equation of the inverse would be x equals 2 to the y, or if you were to write that with y isolated, that would actually be log base 2 of x, if you think of your definition of logs. 2 to the exponent y is x, so these are equivalent statements. So what I need to do to graph the inverse is reverse the x and the y in the table above. So for example, I'm just going to start with this point 0, 1. So 0, 1 is going to become the point 1, 0. The point 1, 2 is going to become 2, 1. 2, 4 on the exponential is now 4, 2. And 8, 3 becomes 8, 3, which is here. If I invert these points, a half over, 1 down, a quarter over, 2 down, and I think you can see the relationship between the points. The points are all mirror images of each other across the line in between them, which would be the line y equals x. Okay, that's always true of inverses. The points are reflections of one another across y equals x. So if the points on the exponential are approaching the x-axis, the points on the new graph are going to be approaching the y-axis, making the y-axis a vertical asymptote. Okay, and so the shape of our function in green, which remember is a log function, is as shown. Alright, so let's just indicate the properties of our log graph. The domain, as you can see, is x greater than 0, and the range is all reals. And the other way to think about it, of course, is that since these are inverse functions, their domain and their range are switched. This is the function y equals log base 2 of x that I've graphed, the inverse of y equals 2 to the x. The 0 of the function, well, the y-intercept became an x-intercept, and so on the new graph there are no vertical intercepts. And instead of having a horizontal asymptote as the exponential had, the logarithm has a vertical asymptote at x equals 0. Let's now consider the inverse of a decay graph. So I have y equals a half x graphed, and I'm going to do the inverse of that, which means to switch x and y. So I get x equals 1/2 to the y, or in logarithm form, y equals log base 1/2 of x. So again, we're going to reverse the points from the table above. So 0, 1 becomes 1, 0. Negative 1, 2 becomes 2, negative 1. Negative 2, 4 becomes 4, negative 2. And negative 3, 8 becomes 8, negative 3. And the points closer to the axes, 1, 1/2 becomes 1/2, 1. 2, 1/4 becomes 1/4, 2. And so I can see the points are approaching the y-axis going this way this time. And again, we see that the two graphs, the exponential and the log, are reflections of one another across the line y equals x, which is always the way inverse functions behave. So our exponential function 1/2 to the x compared with our inverse function y equals log base 1/2 of x. Again, the domain and the range are switched, so x is greater than 0 on the green graph. The range is y is all reals. There's an x-intercept of 1. There's no vertical intercepts, but there is a vertical asymptote at x equals 0. And so we've considered the inverse of the exponential function both in the case of a decay and a growth graph. Now you might remember that with exponential functions c to the x, where c is positive, there is one other shape to an exponential function which is actually linear, and that's when c is 1 to the x. Well, that graph, remember, is a horizontal line. If we were to invert that, switch the x and the y, what we would get is a vertical line, and since that's not a function, we don't consider values of the log for a base of 1. And so to generalize our results, the inverse of the exponential function y equals c to the x, where c is positive, is x equals c to the y, or in log form, y equals log base c of x, as long as c is greater than 0, and as we just discussed, we don't consider for logs a base of 1. And so there are really two types of shapes that we can end up with. If our base is greater than 1, which is the inverse of an exponential growth graph, then we have our x-intercept of 1, and we have our asymptote along the y-axis, and the graph swooping up like so. So that's if c is greater than 1. If we are dealing with the inverse of an exponential decay graph, then our asymptote comes from the top on the y-axis down like so. And so there are two major shapes to the log graph. In both cases, the domain is positive values of x. The range is all reals. There's a vertical asymptote at x equals 0. And there's an x-intercept of 1. Finally, in the case of graphing log functions on the graphing calculator, remember that the log button on the calculator is a log base 10 button. So that's like a base of 10 in this position right here. If I graph that, you can sort of see the graph swooping up. It does have a vertical asymptote along the y-axis if you were to trace. You can sort of get a sense of that, or you can zoom in to get a better view. If I want to graph logs of other bases, what I'm going to need to do is use my change of base rule, which remember is log x, and in this case divided by log 2. So if I type that in, so log x, let's just change this now to divide by log 2. And if you trace along, when x is 1, y is 0, these match the points that I plotted previously. X is 2, y is 1, x is 4, y is 8. So to graph logs of that are not base 10, you're going to need to use the change of base rule. And by the way, another reason why you can't have a negative base on your log or a base of 1 is that when you use the change of base rule, it causes the denominator to be 0.